Hello guys. This is a very interesting video. We are saying application one, electrical circuits. Okay. So we have done how to solve most of the first order differential equations using about five methods, the Bernoullis and so much more. So for this case, we are now diving into the applications of now first order differential equations now to the real world. Okay. So our first step, we are saying application one, electrical circuits. So specifically, these electrical circuits will be dealing on our AC circuits. Okay, alternating current circuits. So as I've listed here, we are saying we have the RC circuit and we have the RL circuit and we have the RLC circuits. So for this case, we are saying for an AC circuit, it's different with a DC circuit. Okay, why? Because we are saying for an AC circuit, it has the current moving in one direction, then again back. Okay, for this case, we are saying for a for a circuit to become an AC circuit, it must have either three of these things. So we are saying it must have a resistor and a capacitor at the same time, or it must have a resistor and an inductor at the same time. Okay, and again we will see a setup where the circuit has all the three resistance, inductor and the capacitor. So for this case we are saying applications to electrical circuits. Okay, so in this video we'll just deal on the RL circuit uh, this video. So our next video will deal on the RC circuit, and on our next video, once we have done second order differential equations, we will look on RLC circuit. So this is for the second order application to circuits. Okay, so this is for the first order. So for this case, we have dealt only with the first order. So we are saying applications of first order differential equations to the real world. So for this case, it's for engineering and maybe physics. We are applying in electrical circuits. So we are saying we have an RL. Okay, another point to remember is the circuit must be in series, not parallel. Okay, so for this case, it's RL series circuits. Okay, so another step, we're saying the inductor is used. Okay, the inductor is used to store electrical energy in magnetic fields where current is passing through them. The capacitor is used to store the charges, and the resistor is offering the resistor. For this case, this our resistor. For this case, this is our inductor. So we have RL circuit, and this is our battery or generator where the current is coming from. So we are saying this equation can be used to model uh, the amount of current in amperes in a circuit containing resistor R in ohms, inductance L in Henry, and the electromotive force uh, E as a function of T in volts. So we are saying the sum of the voltage drop across the inductor. So this is the voltage drop across the inductor, and the voltage drop across the resistor is equal to the EMF. Okay, so we're saying where R and L are constant. So the current IT is called response of the system. So let's get these uh, derivation well. So we're saying the voltage across the resistor is V equals to IR, and the voltage across the inductor is L, the derivative of current with respect to time. So we're saying we will formulate a first order non-homogeneous equation using the Kirchhoff's voltage and current law. So check my video on Kirchhoff's voltage. So we have seen how we can use Kirchhoff's voltage to maybe calculate the current in a circuit. Okay, so for this case, same case applies. So the Kirchhoff's voltage law states that the complete traversal, okay, of the potential changes in a loop of a circuit should equal zero, regardless whether you're going counterclockwise or clockwise. So for this case, we'll just highlight that. So we are saying we are forming a first order non-homogeneous differential equation, linear differential equation using the Kirchhoff's voltage law. So the Kirchhoff's voltage law states that in my video we said we have the EMF rule. So go check the EMF rule. So if the current is flowing in the direction of the E, okay, so the E at this point is this. So we are saying we will say if we traverse from this point, so let me label this as VA. If we traverse from point A and we go in the counterclockwise direction, okay, in the counterclockwise direction, we should get our complete change in potential, the algebraic summation in the potential as VA added that to this is going in the same direction as the EMF arrow, so E1, and then along the lines we don't have the potential changes. So from this point we'll have a drop in the voltage, okay, we'll have a drop in the potential at this point, so should be negative. The potential at this point we have said is L delta I upon delta T, and then at this point again the current is moving to the it's moving along, okay, or through the resistor, so should get another voltage drop at that point as IR, okay. Along the wire there's nothing that's changing, so we should get back to our original voltage, okay. So go check my video on the potential, okay, on the Kirchhoff's voltage law. So we are saying if we transpose this V to this side, we will get E1 should equal, again transpose this, then transpose this again, should equal L delta I upon delta T, added that to Ri, then this VA cancels this VA, so we have this equation, okay. So this is the equation which we are having. So these are first order non-homogeneous differential equation. We are saying E as a function of time, okay, should equal L di upon dt plus RIR, okay. So we have already formulated our first order non-homogeneous differential equation. So we are faced by the problem of how will we solve this, okay. So because this is the first order non-homogeneous differential equation and it's a linear equation, okay. So go check my video on how we solve linear first order differential equations. So for this case we'll have to use the concept of integrating factor, okay. So let's calculate that. So our first step is to get our integrating factor. So our first step is rewrite this non-homogeneous linear equation in terms of the general form. So we are saying we will get di upon dt. I'll divide by L at this point, divide by L, and then I'll divide by L to this point. So I should get plus R over L I, okay, should equal E as a function of T upon L. So at this point we have transformed that differential equation to the form which we wanna operate with. So from this point we are saying these are P of X. Remember, these are P of X. So we'll say our integrating factor. So we'll say our integrating factor mu of X, okay, should equal the exponential raised to the integral of, now we're saying this P of X, which is R over L, okay, R over L, these are P of X. So let me label these as, these are P of X, okay. So these are P of X. Then we should integrate that with respect to time. Why? Because this is current. Current is the flow of charge per unit time. So we are respecting that with current. We are respecting that with time. Okay. So if we perform this integral, we are saying these are constant. Okay. So we are saying this will transform to e raised to r all over L, the integral of dt. Okay, so if we perform this, we should get e raised to r all over L t. Okay, so if we integrate 1 delta t, we should get t. So these are integrating factors. So for us to solve for this system, we are saying multiply all the terms by the integrating factor. So we should go back to our equation and multiply it by the integrating factor. So we say the integrating factor is e raised to r all over lt multiplied by di upon dt, then plus I'll say e raised to r all over lt multiplied by r all over l multiplied by I should give me uh, this point. Okay, should give me this. So I'm saying should give me e raised to r all over lt. Okay, r over lt divided by, okay, so this is l. Okay, so I'm multiplying that by e divided by l. Okay, so from there, so let's perform our integral. We're saying from this point you can see, so if we perform this integral, we are saying this is just simply d dx, okay, d dt, not dx at this point. So d dt, okay, d dt is just the same as now our integrating factor r upon l t multiplied by I should give me uh, e raised to r all over l t. Okay, multiply that by this. Just we said we were dividing by l, so we should get we are multiplying that by that, so we should get e t divided by l. Okay, so let's perform this. So how will we perform this? Take the integral of both sides. So if we take the integral of both sides, we are solving for this. So we should get e raised to r all over l t multiplied by I should give me the integral of this, but these are constant, remember. So it's just this e to the t divided by l. Now take the integral as e of r all over l t. Remember it's dt. Okay, remember it's dt for us to be able to integrate this. So we are saying let's perform this integral. So it's e as a function of time, and remember this e is the EMF of the device. Yeah, so it's the EMF of the ideal device. So it's saying taking this integral, because this is the integral of exponential functions, so I'll just write e raised to r all over l multiplied by t, then I'll divide that by the derivative of the power, which is r. Okay, r all over l. So go check that. So if we simplify that clean, we are saying this will equal e as a function of t divided by l multiplied by l all over r multiplied by e raised to r all over l t. Okay, as you can see, l cancels with l. I should get my answer as e as a function of t divided by r multiplied by e raised to r all over t. Okay, r all over l, not t. Okay, so it should be r upon l t. Okay, plus a constant integration c. Okay, so this should equal e raised to r upon l t multiplied by I. So for me to solve for my own I, okay? So I'll divide by e raised to r all over lt. This whole expression again, divide it by e raised to r upon lt. So this cancels this. I'll remain with my current equal. These will cancel this, and then this will go here. So we're saying if e as a function of t divided by r, then I'll add that to c multiplied by e raised to negative r upon lt. Okay, so from there, so this is our general solution. Okay, so we already solved for this differential equation since this is our general solution. So from this general solution, we usually have our initial condition. The reason being is before the circuit was closed, okay, before the circuit was closed, no current was flowing through the circuit, okay. So we had a time equal 0 and we had the current, no current flowing at that point, okay. So this is our initial condition. So this is our initial condition. Remember the initial value problem, IVP. So this is our initial condition before the circuit was closed. So when the circuit was open, okay, when the circuit was open circuit, we are saying I will go to 0, should equal E as a function of t upon r, then plus c multiply. As t equals 0, this will equal, should get 0 equal e t upon r plus c. Okay, so from this point, solving for c, we should get negative e of t upon r. Okay, so that's our value for c. So let's substitute back inside the general solution. So the general solution was equal uh, I equal e, okay, I equal e divided by, remember this should be let's check please. So we were saying this is e divided by l, okay. So this should be l. So from this point, I'm saying this should be r, not l. This should be r, okay. So we are saying our initial condition is e t divided by r, okay, plus, so we were saying it's plus c, okay, but now we have calculated our c to be this, so it should be minus this upon r, okay. Multiply that by e raised to that, okay. So let's clear this, please don't confuse this. I was just giving an explanation to this. So we're saying it's c multiplied by e raised to negative r upon l of t. Okay, so let's pull out this common factor. So we're saying e of t divided by r into 1 minus e raised to negative r all over l t. Okay, so these are general so these are particular solution, okay. So these are particular solution to this differential equation. So maybe just a quick comprehension to this. We are saying we are applying now the first order or the first order differential equations, okay, ordinary differential equations now to the real mechanistic world. So we are saying the first application, we have done it on electrical circuit. We have seen the RL series circuit and how to, once you have gotten the expression, we should, okay, we should solve this first order differential equation, non-homogeneous differential equation, using the methods of integrating factor, and should get our answer, okay. So in our next video, we'll be looking on the RC circuit, okay. So the RC circuit again will use differential differentiation and ordinary differentiation to get uh, to the final answer, to get to the final expression, okay, of to get to the particular solution on how to solve that differential equation. So please like, share and subscribe to my channel. Follow for more amazing physics math related content. So please like, share and subscribe to my channel. Have a good day.